Welcome, everyone. It's a pleasure to have John Harvey this week. He's at Swansea University before he was in Münster in Germany, and he will talk about estimating the reach of a submanifold.
Thanks very much, Fernando. Thanks for the invitation. Glad to see people. This is the first time I've done one of these distanced seminars. It's taken me a long time to dive in, but here we go. Splash. This is about estimating the reach of a submanifold. So this talk is sort of a mashup between geometry and probability theory. So since we are a geometry seminar, this is a geometry audience, let's get started with some very basic talk about probability theory. So I want to just start by telling everyone what statistical inference is. So it's the process of inferring information about the population from a sample. Okay, so like maybe there's a true fact about the population, like what percentage of people intend to vote for Joe Biden, what percentage intend to vote for Donald Trump. You take a sample and then you attempt to draw some inference about the truth based on what you saw in your sample. And to do this, you need to make some assumptions. You can't just carry out the survey and then draw conclusions immediately from the survey. You need to make some kind of assumption about what's happening underneath. And we call this a statistical model. So let me, for example, draw a picture. Suppose we have the real line. This is the real line here. And I'm given 6 numbers on the real line, like this. And the question is, what's the probability distribution that these numbers come from? Okay, it's not possible to answer the question, what probability distribution do these numbers come from? A reasonable answer might be that it's some kind of bimodal distribution like this. Why not? But it's just as reasonable to assume that there's a bunch of Dirac deltas, right, point masses, here, here, and here. These are all delta masses. It's just as reasonable to assume that that's the underlying measure that the 6 points were sampled from. It's only if you make some assumption about what you think the probability distribution should look like that you can even begin to try to give a reasonable answer. So this is called a statistical model. The statistical model is the set of probability distributions that we think are reasonable to begin with, and then based on our sample, we'll say which one we think makes most sense. So let me try to, return to just moving down the screen. Suppose you have a statistical model, and suppose you have a set of estimators, a set of probability distributions that you think are reasonable. Once you have that, you can start proving theorems about how inference would work. So here's a simple example. Suppose you're trying to estimate the mean. Okay? You have a sample and X bar is the sample mean. The sample has size n. And then there's an underlying truth, which is the population mean is mu, and the data is generated from a normal distribution, which has variance sigma squared. So this is more as a first year statistics question. How well does the sample mean approximate the population mean? And the answer is that the expected error, the expected square error, is always sigma squared over n. So if you put some kind of constraint, say that the model is going to be, we'll look at normal distributions, but with variance no greater than sigma max squared, then that allows you to say that no matter which distribution you've got, right, no matter what mean mu, no matter what variance sigma squared you have, the expected square error will never be greater than sigma max squared divided by n. So that's a first year undergraduate result. And then you can ask yourself, okay, could I do anything better than the sample mean? Suppose I had another estimator for the mean, which is mu hat. Well, it's possible to show that it's also the case that for mu hat, if I look at all the possible distributions, all means mu, all variances sigma squared, the expected square error is always going to be greater than or equal to sigma max squared over n. So that means that the best possible estimator, if I look at the infimum over all possible estimators mu, I will get that it's equal to sigma max squared over n. Sorry for the typo there. Okay, so take the supremum over all the distributions that are in your model. What's the worst case distribution you could be faced with to try to estimate the mean? And then look at all the possible estimators you could use. The answer turns out to be that we could never get a better expected square error than sigma max squared over n. Okay, so that means that this sample mean, x bar, we'll call this the minimax estimator of the mean for this loss function. Okay? Minimax because it has this inf sup in the depth, okay? And it depends generally on the loss function. If the loss function is the way that you say how bad an error is. So we're saying we measured the badness of an error by the square of the difference between the estimator and the true mean. And the particular thing we want to get out of the minimax estimator, often in statistical inference, is the minimax rate. So we see that our minimax estimator performs at sigma max squared over n. So that means the expected error is proportional to 1 over n. So n to the minus 1, that's the rate. As we add more points to our sample, the error gets smaller, and the error gets smaller at a controlled speed. Okay, so let us move on then to talk about some geometry. Right? If statistical inference is the process of inferring some information about the population from the sample, then geometric inference is what we call the process of inferring information about a geometric object from a sample. So by a sample here, I just mean a lot of points that lie on the geometric object or maybe near it. And this is quite a new field of study. What kind of information might we want to learn? We might want to learn about the dimension of the manifold. I'm sure you've all heard of persistent homology, which is a way of trying to obtain information from a set of points about, say, the homology of a manifold. It doesn't have to be a manifold. I'm assuming my geometric objects are. We might want to learn what the manifold itself is. And if we do that, it becomes a bit more complicated. You know, you've got to say, what sort of loss function are you going to use? I'm going to talk generally about the Hausdorff distance. So I produce an estimator for the manifold, which is just some set that happens to lie close to the manifold. You might want a stricter loss function, which also reflects the question of whether or not the answer I give you as an estimator is isotopic to the true manifold, rather than just lying near it. Okay, so what about the statistical model? If I am going to do some sort of inference, I need to put down some kind of constraint. The constraint is crucial. When I said that the variance had to be bounded by sigma max squared, that put a kind of compactness onto the set of probability distributions. It wasn't really compact because I could admit any mean I wanted, mu, but there's a by controlling that nuisance parameter, essentially, the variance, I'm able to have a uniform bound on how well my estimators perform. So what sort of things do I need to control? Well, I still need to control these sort of information about the distribution, but I also will need to control information about the geometry of the manifold, because that is really information about the distribution as well. It's information about the support of the probability measure. And really what this talk is going to be about is about what parts of the geometry do we need to constrain and how can we estimate those parts. Now here are some tricky examples for geometric inference. I've got two closed curves which are sitting in three-dimensional space. But the closed curves are different, right? If I look at their intrinsic metric, they're clearly quite different objects. Right? This point here is far from this point here. This point here is close to this point here. Okay, that's the difference. So what is it that would make it hard if I just had a random sample of points drawn from these shapes? What is it that would make it hard for me to distinguish them? Because it would be hard for me to distinguish them. They're not ordered, the points that I get. They're just scattered around the manifold any old way. And the answer, the obvious answer, I think, is there's these bottlenecks. Okay, one part of the manifold, the lower branch, comes close to the upper branch. Or here, the over crossing part and the under crossing part are close to each other, you see. So these are bottlenecks. They will cause difficulty. Also, if I just have a few points looking like this, and I look at this area of the picture here, there would be nothing in those 5 points that tells me I'm looking at a curve, because if you just take away the black line and imagine the red points, you might think this is a two-dimensional shape, that these are 5 points drawn from something two-dimensional. So the curvature makes it hard to see what's going on, and bottlenecks make it hard to see what's going on. And this is sort of the heart of what's happening. Curvature and bottlenecks together can be expressed in terms of something called the reach of a submanifold. So I'm going to start just with this picture, which shows a one-dimensional manifold. And I've decorated this manifold with a kind of a fringe. Little hairs sticking out all over the place. Normal vectors, really. And as I make them longer and longer, the fringe starts to tangle up. Okay? The ends of the vectors start to come across each other here. Or here we've got vectors coming from this side are starting to meet up with the ones coming from this side. And this picture is sort of the definition of the reach. Let me give a textual definition of the reach as well, which is a bit more dense. If you have a submanifold X, then what you do is you take the delta thickening of X. So you just look at every point in the ambient space that is delta close to a point in X. And then if delta is small, you've got a tubular neighborhood of X. So for any point Y that's in the delta thickening, it's got a unique closest point X, and the line from Y to X will realize the distance from Y to the submanifold. So basically, you've got a metric projection from the tubular neighborhood, the delta thickening, onto the submanifold, and it's well defined. But if you make delta too big, this projection is no longer well defined. So we say the reach of the submanifold is the largest possible delta for which the projection is well defined. So,
sorry, are you assuming the submanifolds are embedded? Is that?
Yes, I am. Yes, if a submanifold were not embedded, okay, so no, I'm not assuming it. Just a submanifold that was not embedded would have zero reach. Yeah.
Okay.
I will always handle embedded submanifolds because the question just doesn't work otherwise, and they will all be connected as well. And in what I'm talking about, they will always be compact, but you can still talk about this in a non-compact situation. So just to show you again, here's the picture. Once you make the fringe too long, in other words, once you make the number delta too big, then you no longer have this unique projection back. Okay, so if I am here, I do not know whether I should project back this way or project back this way. If I am, say, here, then there will be a point here and a point here. They're both going to be equally close. So that is the reach. You could also think of it as being the normal injectivity radius, right? Just like the injectivity radius has in a Riemannian manifold, there's two ways the injectivity radius could arise. One is through conjugate points, which is basically what's happening here, where we're looking at the focal radius and seeing this measurement. And the other is through global issues, which is what we're seeing here at the bottleneck. So what's so important about the reach? It's well established now in the geometric inference literature. I think every paper that I have read where someone tries to draw some kind of inference about a geometric parameter, it's necessary to control the reach. It's an absolutely key regularity parameter. You need some sort of uniform lower bound on the reach in order to calculate minimax rates for anything, right? For how well you can estimate the homology, for how well you can estimate the topology of the manifold, the location of the manifold, anything. So what that means, sort of similarly, is you could say in a low reach situation, then you're going to need a very large sample size if you're going to be able to carry out the estimation. Okay. Just like if you're trying to study whether or not a drug works, if the effect of the drug is only slight, you will need to study many, many patients in order to be confident that the effect exists. Not only does it drive our assessment of how accurate these estimators are, it's also actually crucial to carrying out the estimation itself quite often. So if you try to reconstruct a manifold, in other words, if I give you a bunch of points and you want to put them back together into the manifold, the basic sort of universal way of doing this is to draw a whole load of little balls and then do a best fit, right? Like maybe a linear regression. And find some way of patching all the little lines together into a kind of a manifold shape. And if you draw a ball, but the ball is bigger than the reach, okay, then suppose the true manifold was the kind of manifold I've been drawing all this time. One of these sort of dumbbell shapes with a bottleneck. When I draw this ball here, I capture bits from different parts of the manifold, and then I run into big trouble because my line of best fit runs across the manifold or does something weird. So the actual process of estimation itself requires you to know a lower bound on the reach so that you know what size balls you should draw in the first place. Another thing, which I'm not going to talk about at all today, is that if you have a manifold with small reach, then noise is going to be a big issue. Right? Suppose the sampled points didn't lie directly on the manifold, but only near it. In a case where you have large reach, that's just not really a problem. But if you have small reach, if you have these little bottlenecks, then having any kind of measurement error is going to really tangle the situation up. Okay, so let me define the reach again in a different way. I'm going to consider it to be the minimum of two different invariants. One I'm going to call the local reach, which encodes the curvature information, and that's the focal radius, and the other is going to be the weak feature size, which encodes the global information. And we saw there were two different ways that the fringe of vectors, right, that the tubular neighborhood could kind of cross itself. One was through the focal radius, one was through the bottlenecks. So the reach is going to be whichever comes first. It's going to be the minimum of this local reach that comes from curvature and the weak feature size, which comes from the global information. Okay. So two different ways to do it. And any way you define the reach will contain more or less obviously that dichotomy. So very quickly, what's the local reach? It's to do with curvature. If you have a submanifold, an embedded submanifold, then the simplest way to think about the curvature is through the second fundamental form. The more curved it is, the higher the second fundamental form. And if I take the operator norm of the second fundamental form at a point and take the reciprocal of that, then that gives me the radius of a sphere that I can fit inside the submanifold. Maybe a picture would be good here. Okay, so suppose I'm here at the most curved point. If I take 1 over the norm of the second fundamental form, I will get the radius of curvature. And I'll be able to fit a ball in here that actually fits. One that I've drawn on a blackboard rather than on a drawing tablet. Will fit in there and be tangential, and everything works nicely. And the same just works perfectly in higher dimensions. Okay, so you can express the local reach as the reciprocal of the norm of the second fundamental form. And you look over all the points P in your submanifold, and whichever one is most curved, that will define the local reach. What about the weak feature size, this global issue? Well, if we go back to work of Grove and Shiyahama, they defined the idea of a generalized gradient field for the distance from a submanifold. So let's say d sub x, that's the distance from your submanifold. And then you can take a derivative of that to get a gradient. So here's the picture. Suppose you have some point P that is not on the submanifold. What direction would you travel in order to increase distance from the submanifold? And the answer is that what you should do is you should find the point nearest to P on the submanifold. Let's call it Q. And then if I go from Q to P and keep going, that increases distance. But what if the point Q is not unique? What if there are 2 points? Well, then you simply do your best to get away from both Q1 and Q2. Really what you do is you take an average and you travel in that direction. And if you travel in this direction, you're not going to get away from the submanifold at unit speed for every unit you travel. It's going to depend on this angle here. So that's a sort of a gradient field that you can use. It tells you how to increase the distance from the submanifold. And then you can say you've got a critical point if you're not able to get away from the submanifold. So I've got a couple of pictures of what that would look like. Here's one like this, right? So suppose these are 3 parts of the submanifold. They'll join together, giving you a kind of a fidget spinner shape, as my 8-year-old says. And if you look at the central point here, this point is a local maximum in terms of distance from the submanifold. The gradient field, nabla x, basically looks like this. And here's another one. If we look at the more classical bottleneck example that I've been drawing from you, in this case, the gradient field points away from the submanifold here. When you're in the middle, the best way to get away is to point in this direction. So what's happening here is that you have a saddle point, more or less, for the distance. So these are 2 different types of critical points for distance from a submanifold. So we'll use that to define the weak feature size. We say the weak feature size, look at all the critical points. So let curly C here is the set of critical points. Look at every critical point that isn't in X. If you're in X, you're always critical. And look at the one that is closest to the submanifold. And we say that distance is going to be the weak feature size. Now, what happens in this case? At the first critical point, it turns out there's going to be 2 shortest paths traveling to it in opposite directions. So you have the chord crossing a bottleneck. I think that picture, no, I don't have the picture. It's the same picture I've been drawing again and again. The point is that the fidget spinner configuration of 3 or more points, that won't happen, because in order, let me draw it again, in order to join up these 3 components here and bring them back together, you actually have to introduce too much curvature so that you end up seeing the reach here and not here. Okay? You end up with curvature being the most important thing and not this 3-way bottleneck structure. So if a bottleneck gives you the reach, it will always be a simple bottleneck like this. Okay, so that is all the definitions we need. Here's some examples, really basic examples. Suppose you had a flat plane, then that will have infinite reach. If you have a flat plane inside Euclidean space, then every point has a unique nearest point on the plane. So there's no curvature, there's no bottlenecks, the reach is infinite. If you take a sphere of radius r, then r is the reach. So in this case, r is the radius of curvature, but also if you look at 2 antipodal points on the sphere, that creates a kind of a bottleneck as well at the same time. So it's not really a dichotomy between bottlenecks and curvature. Sometimes you can have them both coinciding. The curvature gives you reach r, but the bottleneck across the sphere also gives you reach r. And then for a submanifold to have 0 reach, it might be that it's only immersed, as we discussed, but if it's embedded, then it will have to be with some sort of singularity. Okay? Any C11 embedding will have positive reach. But if I look at something like the absolute value of x to the power of 3/2, this is not a C11 function, so it's got a singularity at the origin there. And the point is that the tangent directions are changing too sharply for you to fit any ball into that little corner at the origin. Now, here's our approach. Theorems that I'll show you later are all joint with Clément Berenfeld, Marc Hoffmann, and Ravi Shankar. Here's our approach that we came up with for estimating the reach. We look at something called the convexity defect function. And the convexity defect function measures to what extent a manifold is not convex. No compact manifold can ever be convex because it has to curve around on itself. But if you look at it at a small enough scale, it looks almost linear. So it's not that far from convex if you look at a little part of it. So this is a way of quantifying that. What we'll do is take any subset of x, which is sigma. Okay? Sigma is compact, it fits inside a ball, and we can use that ball to define the radius of sigma. Okay? So we've got a way of saying what the radius of any subset is. And the subset lives in Euclidean space, so it's got a convex hull. Right, here's a picture. I've sort of dropped 4 balls of radius r onto my manifold. And you can consider the piece of the manifold that lies inside the ball, consider all of that to be sigma. And then we've got the hull of sigma for each one of these. Right, so over here, in the top left, you can see this part of the manifold is very flat. So here's sigma here. Sigma looks pretty flat, so its convex hull is quite small. Over here, sigma is very curved, so it's got quite a big convex hull. And over here, sigma has jumped a bottleneck. Belongs to 2 different components, creating this massive convex hull of sigma there. And what you do with all these convex hulls is you put them all together. Consider every possible subset sigma, which has radius no more than t. Take the convex hulls of all those sigmas and then stick them all together into one great big set. We're going to call that the convex hull of x at scale t. right? And use that to define a function. For different values of t, we get different convex hulls, and we look at the Hausdorff distance from the hull to the original manifold. I'm not sure if everyone knows what the Hausdorff distance is. All this means is how far away can you get within the hull from the manifold itself. Right? What point in the hull is furthest away from the manifold? And that distance is the Hausdorff distance from the hull to the manifold. So you're asking yourself, this process of taking these convex hulls of little balls, how far away from the manifold does that get us? And here's the picture again. All these solid red patches and more from all the different balls we could possibly imagine. Take the union of all those red shapes. It would have been interesting to actually try to figure out exactly what it looks like. But I mean, it's going to just be a kind of thickening. Where the manifold is fairly flat, it's not going to thicken up that much. But where the manifold is curved, the thickening is stronger. So you just thicken up the entire manifold using this convex hull procedure, but then you also have this bit that goes across. So what sort of properties does this have? Well, if you looked at balls of radius 0, nothing would happen. So this convexity defect function starts at 0. The bigger you make the balls, the more sets you're considering, so the bigger the convex hull gets. So as you increase t, you will increase the distance from the convex hull to the submanifold. This is a non-decreasing function. And eventually, the entire submanifold itself will be a subset of whatever given radius you get to. And at that point, the convex hull at that scale will in fact be the entire convex hull, and things will stop increasing. Things will level off there. Very important is that we have a kind of stability property. If you have another set, x tilde, doesn't have to be a manifold, just any set x tilde, this convexity defect function can be defined for any compact set. If x tilde lies near x, then it will have a similar convexity defect function. So the stability doesn't tell us that hx tilde of t lies near hx of t. It just tells us that if we look at a number close enough to t, between t minus epsilon and t plus epsilon, and put that into hx tilde, then we'll get something close to hx. So let me draw just two graphs that are similar in this metric. Here's maybe one convexity defect function. They don't have to be continuous. And here's another, which lies very close, but then it extends a bit further this way before it jumps up. We can say that these are quite close because even though there's a big difference here, a big vertical difference, if I went back in time slightly and then went down, the vertical difference wouldn't be so big. It's sort of how far away are the two graphs rather than how far away are the two functions from each other. That's the stability property. And it turns out it detects critical values of the distance function. So it's going to detect bottlenecks. If you're at a critical value of the distance function, it's not too hard to see that that's a fixed point of the convexity defect function, that h sub x of t0 will be equal to t0 at critical values. And then the fifth one, the fifth tricky one, is this quarter circle bound. So let me do this as a picture. Suppose here's t. Suppose this value here is the reach. Okay. 0.4 actually tells us that h sub x of t will always lie below the diagonal. Always has to. What I meant to do, shade all this out. Okay, so tool out again. Okay, so you're not allowed to go above the diagonal. But what this is telling us is that if I draw a quarter circle with radius or centered here, you're not allowed to go above that either. So all this area is off limits too. So any convexity defect function has to live under here. And what we showed is that the second derivative of the convexity defect function is the local reach. So this is sort of the key, right? Or rather, the second derivative is the reciprocal of the local reach. Now, I just told you that the convexity defect function wasn't continuous. I just drew you some graphs with jump discontinuities. So what am I doing talking about the second derivative at 0? What I'm doing is lying. Here is the full statement of the theorem, that there is a degree 2 polynomial that approximates the convexity defect function. So it doesn't really have a second derivative. It has what's called a pointwise second derivative at 0. So I can say that near 0, the convexity defect function looks like a quadratic. 1 over RL is the second derivative of that quadratic. And the error term is, in fact, this is very important, degree 4. Okay. If the submanifold is only C3, then there will be a cubic error term. But if it's got higher regularity, there's no cubic error term. We could say that the third derivative at 0 is equal to 0, provided you have at least C4 regularity. If you only have C3 regularity, you can't make any claims about the third derivative. So this means I have these two propositions. The tricky proposition that tells us that the convexity defect function gives you the local reach, that the curvature is encoded there in the behavior near 0. And then a trivial proposition. We said that critical points correspond to fixed points of the convexity defect function. So therefore, the first critical point is the first fixed point of the convexity defect function. Okay, so two completely different ways that the convexity defect function gives us information about the reach. The local reach comes from behavior near 0, and the weak feature size comes from fixed points of the function. Right? Local information happens locally near 0. Global information could come anywhere. Right? It comes from points of intersection, I say. So where does the graph of H intersect the diagonal? At that first intersection, which isn't 0, then that's your weak feature size. Okay, so how can you use all this to estimate the reach? And the trick is to find some x hat that lies near the submanifold X. And there always is some way of choosing an x hat, because if you've got a set of points and you've got a lot of points, then there'd be nowhere on the submanifold that's very far away from one of your sampled points. So that means you could use the point set as x hat, and it will be Hausdorff close to the true submanifold X with high probability. Then I could look at the convexity defect function of x hat. I'll call that h hat. And I know that h hat and h, they've got to be quite close by the stability property. So here's the workflow. Submanifold X, it's got a convexity defect function h. From h, I can deduce the reach. Running parallel to that, I've got some x hat, which is epsilon close to x. It's got a convexity defect function h hat. If I study h hat, I should be able to get out an estimator or hat for the reach. But I do have to build the epsilon in, as we'll see. I can't just get or hat directly out of h hat. I need to get it out of h hat and epsilon, using, as I said, the stability property that we have, that h and h hat cannot be very far away from each other. So we'll have to find an estimate for h double prime of 0. That will tell us the local reach. And then we'll also have to look for intersections between h hat and the diagonal, and that's going to tell us what's going on with the weak feature size. They won't be true intersections, they'll just be approximate. So how do we approximate the local reach, which is 1 over h double prime of 0? Well, we just use basically a central difference formula for the second derivative. Because we know that the first derivative, because we know h prime of 0 is equal to 0, we're able to use sort of something that looks a bit like a central approximation formula to approximate h double prime. So we choose a step size delta, we plug that in, and we get our estimate back. So what's the error going to be? Well, if you've taught any numerical approximation, you'll know that this is a particularly thorny situation, right? As delta gets smaller, as the step size gets smaller, yes, of course, things get more accurate. But if you've shown this to undergraduates, you might have done it in an Excel spreadsheet where you show that as you make the step size really, really small, the computer no longer handles the numbers well, and truncation errors begin to make things worse once you get really small. Now, we don't have truncation errors because this is pure mathematics, but what we do have is the epsilon error. It's not h here. If we were estimating the second derivative of h by putting h itself in here, then we would just have this delta squared error term. But we're putting in h hat, which has a deviation of epsilon, so we get this term here. The bigger epsilon is, the greater the error. And also, as we make the step size smaller and smaller, epsilon gets more and more important. So you have to choose your step size correctly. And the way you choose your step size is just to balance those two terms, those two different error terms. You got to balance the epsilon delta to the -2 with the delta squared, which you do by picking a step size that is epsilon to the power of 1/4. So that gives you a way of controlling the error. And if it was C3, because you would no longer have this information about the third derivative of h that we had before, the error is a bit worse. Okay, so this is the result for how you get h double prime of 0 estimated out of h hat. Now, here's a sort of particularly juicy part, is how do you estimate the weak feature size? Okay, we're looking for intersections with the diagonal. The first critical point happens when the graph of h, it does whatever it does, and then at some point, eventually, bang, it must hit the diagonal. That point is going to give us the weak feature size. Now, we're not looking at h. Okay, that's h for the submanifold itself hitting the intersection. We're looking at something a bit like h. It's a graph that lies near it. Well, it's non-decreasing, so it doesn't do that. Ignore that. It does whatever it does. Right? And in this case, maybe it never hits the diagonal. And the problem is, because the red line I've drawn, it got up close to the diagonal here, and then it just hung around for ages, getting closer and closer really slowly, until eventually it did hit the diagonal. There's no mathematical way that I can see to say how long that might take. So that means there's no way to say how good is an approximate intersection. How close should the blue line get to the diagonal before I can say, I think I'm near the intersection now? Could take forever for the red line to get up to that intersection. Not literally, because it's compact, but I don't see any way to bound it. So what am I going to do? Well, it's not give up. It's to remember that there was also this quarter circle band. We said that if you did a quarter circle, which had radius the reach, then that also provided a band. And is that quarter circle band, is that driven by the local reach or is it driven by bottlenecks? And the answer is that it's driven by the local reach. So this proposition is just the original statement that there's a quarter circle band, but instead of the reach being the radius of the quarter circle, I'm now saying the local reach is going to be the radius of the quarter circle. So let me draw here what's going on. Let's say here's our graph. Here's the diagonal. We're not allowed up here. Here's the local reach, which means that we're also not allowed up here. But we will be allowed get up there in the following situation. Say here's hx, and then it gets to this point here, and say this is the weak feature size, and there's a bottleneck. In that case, we will suddenly be allowed to violate the rule and be allowed to get up here. Because this quarter circle band actually only holds before you hit the reach. So this little segment here is accessible by h sub x. So in other words, if you have the weak feature size being less than the local reach, as it is here, you cannot have the phenomenon I drew for you of the graph of h getting close to the diagonal and dawdling and slowly making its way to the intersection. No, you have to have a jump discontinuity. The graph does whatever it does until it gets to the weak feature size. And then in order to get from below the quarter circle up to the diagonal, it must jump. And that sharp jump means that as long as the weak feature size is lower than the local reach, you will easily be able to see in, say, let me do in yellow hx hat, it's going to do its thing. Here it comes, and then it comes up to here. And you will see, okay, at this point, we got close to the diagonal, and we know that must have been an intersection because you're not allowed to get up there into that above the quarter circle unless you are reaching the diagonal. The only way to get up there is to make that jump. Okay, so the idea is we can do an estimator here. What's happening in this estimator? I'm saying that h hat has to be close to t within 3 epsilon. That's sort of the tolerance for an intersection. And I have to start not at 0, but some distance away from the origin, because otherwise I would be underneath the x-axis and none of it would make any sense. The key point is now I have a way of defining my estimator for the weak feature size. I can control the error. As long as the weak feature size is far enough away from the local reach by some number alpha, then I can control the bound in terms of epsilon. If it was too close to the local reach, then you would have, let me just draw it all again. I'll just make a tiny drawing. I don't know if any of you can even see this. If you were right up here, then because the quarter circle is almost vertical, you wouldn't be able to get much precision. So that's why you need this rule that the weak feature size has to be reasonably well separated from the local reach. So now you have a bound in terms of epsilon for the weak feature size. You have a bound in terms of epsilon to the power of 1/4, I think it was, for the local reach. that puts everything together. So sort of to summarize the statement, say you have a submanifold with regularity ck. You need to bound all the differentials of the embedding, because that's how you take advantage of the ck regularity, is by saying the manifold can't be too wiggly by bounding the differentials. We can't let the reach be too small. That has to be part of our statistical model. If the reach is small, it's hard to estimate the reach, which is hard luck. And the probability distribution mustn't vanish, and it mustn't have any infinitely point masses. If you put that lower bound in the probability distribution, for technical reasons, that actually gives you an upper bound in the diameter of the manifold to do with volume control. So that gives you a sort of an OR max as well as an OR min. And then what you do is, to get the best possible result, instead of using the point cloud, which is not a great estimator for the manifold, you use we'll use someone else's estimator, which is considered the best possible estimator for the manifold. And what they do is, if you have a bunch of points, they just try to fit polynomials through like this. And if you fit polynomials, you get epsilon to the k closeness by taking advantage of the ck regularity. And this estimator for the manifold isn't a manifold, it's just a bunch of patches sitting on top of each other. But it's Hausdorff close to the original manifold, and that's all we wanted. It's not particularly easy computationally, so this isn't a very good way to estimate anything. Okay? But if we look at how it works, the performance of the estimator is essentially at a rate minus k over d. And the best possible theoretical performance they've shown is minus k over d. So it's essentially optimal. There's this log factor here, right, which probably is present in the lower bound. This is probably the best rate of convergence you can get for finding the submanifold. So we're going to take that estimator, plug it into our machinery, and we're going to get our own bounds. I'll just look at C4. We find that we can get the local reach with minus k over 2d, and we can get the weak feature size with minus k over d as our rate. And this beats previously obtained rates. Okay, so this is an improvement. And we also look at the theoretical lower bounds, which had been found before. Minus 1 over d is the best lower bound that had been obtained in C3. And we agree with that, but with higher regularity, instead of 1 over d, now it's k minus 2 over d, where k could be higher. Okay, so what did we get? We got an estimator that performed at k over 2d, which is not the same as k minus 2 over d as soon as k gets to 5. So there's something to find out there about whether you can get a better reach estimator. Why is it k minus 2? Well, the metric is ck, curvature therefore is ck minus 2. So this is kind of the best you could ever do. But I don't see how you could do that well unless you sampled the most curved point. So I think that's an unreasonably good estimator. I don't think that this is a sharp theoretical bound. On the other hand, I'm not sure that the estimator we have is the best, because I don't have any reason that I can give you for why k over 2d makes intuitive sense. Okay, so I think this is very open, and that's something I'm really interested in getting into. Our estimator is optimal if there's a bottleneck. It's only curvature that is really tricky, right? Because we're not just saying how do you estimate curvature, we're saying where is the most curved point and what is the curvature there. So that's really it. The point is, this is quite a delicate thing because you're trying to estimate a second derivative. So what we've done is we've found a way to define the reach within a more stable object, which is the convexity defect function, and then choose a good scale to study the convexity defect function at. Okay. And there's more work to do in terms of looking at the local reach. What's the best way to do it? And it would also be really interesting to find what's called an adaptive estimator. So our estimator because it relies on a Marian-Levrard's manifold reconstruction with all those polynomial patches, you need to know what OR min is to draw the little balls and fit all the polynomials. I'd like to be able to use HX to find an adapter that didn't rely on OR min and could just figure it out for itself. And then also computational efficiency would be really interesting. We're relying on this difficult optimization problem and calculating convex hulls, which is not easy either. Okay, so I will leave it there. Thank you very much for having me. I hope you've enjoyed it and happy to hear any questions.